At its core, a computer is a machine that primarily performs arithmetic operations. The heart of the computer itself, the central processing unit, is made up of a series of integrated modules, like the control unit, the arithmetic logic unit, registers, buses, that together with the memory allow for timely execution of a host of both arithmetic and memory modification operations. Breaking it down even further, each unit within the CPU is made up of a set of logic gates with a certain number of input and output terminals. It's the arrangement of these logic gates that, according to Boolean logic, actually performs these operations. But of course, these gates aren't conscious of what they're doing. Each specific output is the result of electromagnetic forces interacting with smaller electrical components in the logic gates, like resistors, transistors, and diodes, with these parts themselves being made up of base materials and elements. At this level, it's quite obvious that computers are very physical machines, and we call this physical arrangement of things computer hardware. Now, normally modules inside of a computer aren't designed at this level of resistors and transistors, but back here at what is called the register transfer level, a register being a high-speed memory storage unit that keeps hold of certain values within these different modules. Registers are also found in nearly every component in your computer, like in the memory or I/O components. The CPU is designed so that through certain input values, called CPU instructions, register or memory values can be changed by the results of arithmetic operations. A piece of software, as examined previously, is mainly a list of CPU instructions with some other data that is placed in memory. Running the program consists of the CPU fetching and executing these instructions. So software is nothing without hardware. At its heart, it's just a simple list of hardware commands. But that doesn't make hardware better or unique from software. Take a look at this Windows 95 computer. It has its own CPU, memory, I/O ports, and everything else that makes it a home computer. Or does it? This computer is actually just a virtual machine, i.e. the physical hardware of this computer is being simulated through software. The end goal of hardware is usually to have a machine or circuit that executes some or many mathematical functions. If the hardware we're talking about is a general purpose computer, then specifically the CPU is designed so that it can perform all kinds of calculations. And then software is a list of what math the computer needs to do to reach certain outputs, whether that be finding the square root of pi, changing an I/O signal, or answering the question that everyone wants to know, what color should this pixel be? But how does hardware, a thing that just sits there like a rock, actually do math? Let's take a look back at those logic gates from earlier. First, let's examine the AND gate. It takes two binary inputs, let's call them A and B, that can have a single bit value of either 0 or 1. If both A and B are 1, then the output of the logic gate is also 1. In any other circumstance, the output is always 0. If we wanted to do the same process in a high-level language, we could write something like if A and B, then whatever would come after that. Using an OR gate is like writing A or B, and so on for XOR, NAND, NOR, and XNOR. Through simple Boolean logic, we can also do binary math. A 1-bit adder, otherwise called a half adder, can be created using only two logic gates. That will give us two outputs. A XOR B gives us the ones place sum, and A and B gives the carry output, which, if 1, means that this bit should be added to the next position. In our case, it would be added to the 2's place. If we want to expand this adder to include a previous carry signal, then we can add a few more logic gates to include this carry bit in the calculations to find the new values for these 3 bits. This is known as a full adder. With these two modules put together, we can have a complete 2-bit adder. We can also keep adding full adders in to expand the number of bits that we can add together. In a modern CPU, being 32 or 64 bits long. Although this is the simplest kind of adder, the adders in your CPU have some additional logic gates that provide certain optimizations, but the basic concept is still the same. All arithmetic is possible via Boolean logic gates, gates that are made of components of base materials. In a gross simplification, it's like saying if we just arrange sand in the right way, it just does the math for us. But again, in reality, none of this is an accident. All these things down to the very last transistor are designed to do exactly the function it needs to do. All hardware is the arrangement of physical elements so that the electromagnetic forces that are the input will produce a certain output. This is physical programming. There is really not a lot of difference between a compiler turning your code into CPU instructions and a human compiling an equation into a physical arrangement of logical components to achieve the same results. Because hardware and software are quite literally virtually interchangeable, today's hardware is near always designed through software. In fact, it's often designed in almost the same way that software is. What we're trying to design here is called a digital logic circuit. And for the last half century, circuit designers have been using hardware description languages, HDLs, to design and structure the behavior of logical circuits in software. The most popular HDL is Verilog, invented in 1984 by Prabhu Goel, Phil Morby, and Qilai Huang. Verilog's C-like syntax made it a popular choice for designers to begin using, as C was already widely used at the time. Different parts of a Verilog design are broken into modules, which, usually through some coordinated clock signal, work together to define the functionality of an integrated circuit. The end goal of hardware design is often to produce an application-specific integrated circuit, a custom chip designed for a certain use, like a chip that converts binary to BCD code, or a chip that runs the logic for your electric bull equipment. The circuit's functions are programmed in an HDL and are then analyzed, synthesized, and tested both through simulation and physical testing on a field-programmable gate array. FPGAs are integrated circuits that are designed to be reconfigured by the end user. Within an FPGA is an array of programmable logic blocks that can be configured to perform certain logical functions, allowing it to act as a logic gate or like a memory element such as a register. An FPGA chip is reprogrammable hardware. This is different from a Raspberry Pi, which is just a microcomputer, essentially no different from your home desktop, or an Arduino, which is a microcontroller. It compiles your code and executes a list of CPU instructions, but the hardware itself does not change. When a design is configured onto an FPGA, the logic blocks are reconfigured to the schematics of the compiled HDL design, resulting in a physical change within the chip. The hardware then acts as an ASIC, or in other words, there is no CPU running instructions. This is real hardware physically executing whatever logic was implemented. Designing an FPGA often requires the use of an FPGA board, which has numerous I/O pins that can be given some form of functionality, whether it be connecting them with buttons, LEDs, buzzers, displays, or other I/O pins. To fully program these devices, proprietary software from the hardware manufacturer is used, usually being Xilinx ISE or Vivado Design Suite for AMD's Xilinx FPGAs, or Quartus for Intel's Altera FPGAs. I bought this Max 2 CPLD Altera EPM240T kitboard for around $15 off some Chinese website, with the only catch being that there's no formal documentation for this board, just a couple of project files from the guy who sold it to me. Now, I'm not saying that the only documentation is in Chinese. I looked. There just isn't any documentation at all. I don't even know if Today's Start is supposed to be the brand or if it's just an inspirational message.
รวยปัญญาพัฒนาฉลาดชาติเจริญไปถึงไหนแล้วก็ไม่รู้แค่เลิกเล่า
To demonstrate how FPGA programming works, I'm going to design a real-time clock displayed on this 8-segment, 7-segment display. After setting Quartus to target this specific FPGA, I began by defining my Verilog module with a 1-bit clock input signal, an 8-bit 7-segment representation signal, and a 4-bit display control signal. Since the internal clock of the EPM240T runs at 50 MHz, an internal counter register and some related variables to keep track of hours, minutes, and seconds were created as well. Since the display has a refresh rate of 60 Hz, then within each 16 millisecond window, all 4 digits of the 7-segment display should be refreshed. This is done through switching the digit control signal once every 4 milliseconds, which tells the 7-segment display which of the 4-digit segments to turn on and whose pattern will be set based on the current input from the 8-bit representation signal. After writing some of the other clock logic, the module can be turned into a symbol file, and a new block schematic diagram file can be created. Here I can add my module, which has its associated inputs and outputs. Then I can add input and output pins, wire them together using proper naming syntax to convert data buses to individual values, and then associate these pins with the correct I/O pins on the FPGA. If everything works correctly, I can compile and then set up the hardware on the board. And now I have a clock running off hardware. I can unplug this cable and turn it off and on again just to prove that this is real configured hardware. But while a broken clock is right twice a day, a clock set wrong is never right. So I need 2 more inputs, one to set the hour and the other to set the correct minute. Going back to my Verilog file, I can quite easily add 2 more input signals, and some other additional logic and timing. Then after I reconfigure the symbol file and wire the new additional inputs to the correct I/O buttons, I can reconfigure the hardware again, and it should function like a normal clock. Again, this clock isn't running off of software. There's no CPU running the instructions to keep track of everything. This is a physical circuit providing real-world functionality. Also not very relevant, but I found that 7-segment display digits are also included in Unicode. Remember to subscribe if you'd like to see more, and until next time, thanks for watching.